Thank you all for coming here. It's been, I think the last seminar I gave at Monash was in person, and then I never got to give an in-person talk until basically after the pandemic. So it's really nice to be back. So today I'm going to be talking about long-lived neutron stars. So it's a little bit about what I did in my PhD, but more about what I'm doing now and sort of current project. So really the title is Long-Lived Neutron Stars Born in Binary Neutron Star Mergers, and this is work that I did as part of my PhD and I'm doing now. This is a schematic of a binary neutron star merger and just showing the overall sort of pathways you can take. And so in panel A, and this is made by Carl Knox, who's a resident graphic designer over at Swinburne, so he's a wonderful artist. As you see, as you go along, you'll notice that the quality of the slides and the plots degrade significantly, and that's because I don't have Carl Knox's slides and graphics to fall back on. So in panel A, you've got a merger of two binary neutron stars. So of course, as the emission of gravitational waves, the binary gets closer and closer, and so you eventually merge, and then that merger is shown in panel B. And then immediately you sort of have multiple branchways you can take, and these branchways dictate what you're actually going to see from an electromagnetic and gravitational wave perspective. And these branchways depend on basically two things: the mass of the binary, so what the total mass of the binary was, and therefore what the mass of the remnant object is going to be, and something known as the Tolman-Oppenheimer-Volkov mass, which is the maximum allowed non-rotating neutron star mass. And so over here, you're going to immediately, if you take this pathway, which is anywhere, if you have a binary remnant mass which was above sort of 1.5 times MTOV, you're going to immediately collapse into a black hole. And now that immediate collapse into a black hole might have some accretion disk around it. That accretion disk might be able to launch a jet, and I'll get to all those things a little bit later. But now if you're a little bit below that threshold of about 1.5 times MTOV, you can still support yourself against gravitational collapse through differential rotation. And you end up making this thing known as a hypermassive neutron star. We're amazing with names. And so these things are differentially rotating, and that differential rotation can give you an additional bit of support and sustain you against gravitational collapse for a little bit of time. And so this neutron star, this hypermassive neutron star, is differentially rotating. That differential rotation is quenched on sort of thermo-alphane timescales, and that support is lost sort of on an order of 1 second or so, or shorter. And if you're sort of above sort of 1.2 times the MTOV, the Tolman-Oppenheimer-Volkov mass, you're going to have a little bit of a delayed collapse into a black hole, and that's shown in panel E over here. And now, if you're actually below 1.2 times MTOV, you can end up supporting yourself against gravitational collapse through just rigid body rotation. So after the system stops differentially rotating, it's going to rotate through rigid body rotation, and that rigid body rotation can also give you a little bit of support, but it can only support masses up to sort of 1.2 times the non-rotating limit. And so you end up making the system known as a supramassive neutron star, not supra for some reason that I've forgotten, and doesn't really matter. It's just another evidence of why we are silly with names. So this supramassive neutron star is going to lose its rotational support on long time scales. The time scales are not exactly certain, but they depend on things such as how fast this thing is spinning down initially and how fast it actually loses that support, because once it loses the support, if it's above MTOV 1.2 times MTOV, if it's above this Tolman-Oppenheimer-Volkov mass, it's going to produce a black hole. And now this time scale could be anywhere up to 10 to the 5, 10 to the 6 seconds, but again, it depends on the initial conditions of the neutron star itself. And now if you had a binary that was actually producing an object which was less than the Tolman-Oppenheimer-Volkov mass, you're going to end up making an infinitely stable object, an infinitely stable neutron star. And so the talk today is mostly about these guys, mostly about long-lived neutron stars, as I call them, which are basically anything that's going through this pathway of making a supermassive neutron star or an infinitely stable neutron star. And the reason I go through this pathway in particular is, well, A, I spent most of my PhD doing that, and B, this pathway can dramatically alter the multi-messenger signatures you're going to have in a binary neutron star merger. So this is a plot from Asensi et al., which is a really nice review article written by Stefano Asensi, just showing the sort of electromagnetic observables of a binary neutron star merger. And what's happening at the heart of this system can basically change all these different observables. And so, for example, you have a central engine. In this case, it's a black thing, which is just showing the bias of the authors. But you have an accretion disk around it. That accretion disk launches a jet. It may or may not be able to launch a jet, and I'll get to that later. But ejector from the accretion disk can make some sort of kilonova. That ejector can, do R-process nucleosynthesis and makes your kilonova. In the process of the merger itself, you have tidal ejector, so basically ejector from the tidal tails. That gets launched on the equatorial plane predominantly. That's what we see from numerical simulations. And that has typically got a low electron fraction, and that ends up making your red kilonova that we saw, for example, for 1708-17. In the course of the merger itself, when you have two bodies contact, you end up shock heating the ejector, and that ejector gets predominantly launched along the polar regions, and that makes your blue kilonova because it's much more electron rich, which means you can't produce as many heavy lanthanides, which means your kilonova appears bluer. Now, that jet, whatever that jet was that gets launched from the central engine, whatever that central engine was, makes its way through the polar ejector, and it produces this sort of thing called a cocoon, which is basically just whatever the jet interacted with, it really heats it up, it really sort of makes this little blob, and this little cocoon can produce something known as a cocoon shock breakout, which is basically gamma ray emission or high energy X-ray emission that's just being produced by this superheated blob of ejector. Now, in some cases, or at least we know for certain for 1708-17, the first binary neutron star merger, the jet actually made its way out of the cocoon, in which case internal dissipation, likely internal dissipation in the jet itself, produces your GRB prompt emission, which is the gamma ray burst we see. And then at later times, that GRB jet interacts with the ambient interstellar medium and produces what we call a GRB afterglow. And this is the broadband energy we see following almost all GRBs. It's the X-ray afterglow, the optical afterglow, etc., and so forth. On much, much longer timescales, so this GRB afterglow happens on timescales such as 10 seconds, on anywhere up to a few days after the merger, and what timescale you see it on is dependent again on the viewing angle, for example. But on much longer timescales, you get this kilonova afterglow, which is basically the exact same physics as your GRB afterglow. It's your but instead of a jet interacting with the interstellar medium, it's the ejector itself interacting with the interstellar medium and again producing synchrotron radiation. And now, what happens to this little system over here? In this case, it's a black hole, but if this was a neutron star, that can radically alter all these different observables. And so really, my interest is trying to understand what this sort of connection of this engine is to all the observables, and then going back and forth and trying to work out what can we tell from observations about them. So in particular, whether you can have a jet or not, whether you can what happens to the kilonova, what happens in terms of gravitational wave emission, because the black hole gravitational wave emission is going to be very different from if there was a neutron star there. The same thing with, for example, if there's a radio remnant and other things and so on. So let's go through an exercise which is basically how many mergers do we actually expect to produce a long-lived remnant? I've just talked about this sort of pathway, but a natural question to ask is, okay, well, do we actually ever expect this to happen? And so to do this, we actually need two ingredients, and unfortunately we don't have either of them. But we need to know the neutron star mass distribution, so what the binary neutron star mass distribution actually looks like. So, is it, a Gaussian peaked at 1.4 solar masses, or is it a bimodal distribution? And we need to know the equation of state, because the equation of state dictates what MTOV is, the Tolman-Oppenheimer-Volkov mass. So now, before we observed GW 190425, the second binary neutron star that LIGO, Virgo, Kagra observed, we were actually reasonably sure what the binary neutron star mass distribution looked like. And that was predominantly because we knew that there were about 18-20 systems in our galaxy, double neutron star systems in our galaxy, that all followed a reasonable sort of distribution that we were pretty sure applied to everything else as well. And in fact, 1708-17 also matched that distribution really well. But then 1904-25 happened, and that just threw a spanner in all works. So this is a plot showing the double neutron star mass distribution, so for each individual object, and the mass distribution for every neutron star in our galaxy, so even those that are in any other binary, so white dwarf binaries or anything else. And so you see that the double neutron star mass distribution is really nicely sort of, this histogram really nicely, peaks around 1.38, 1.4. There's this really nice paper from Kizilton et al. In 2013, which shows this constraint. And then 1708-17 happened, and if you look on the right-hand side, I'm showing the chirp mass instead of the neutron star mass, which is the well-measured property from gravitational waves. And the GW 1708-17 chirp mass fits really nicely in this little Gaussian. But then 1904-25 happened, and this 1904-25 is like a 5 sigma outlier from this distribution. So what on earth is the binary neutron star mass distribution? So in 2020, we wrote a paper where we just decided, okay, how about we play this game where the binary neutron star mass distribution is essentially two Gaussians. One Gaussian that well follows the distribution we see locally in our galaxy, and another Gaussian which is centered around other neutron stars in our galaxy, so neutron stars that are in other binaries, which is well explaining 1904-25. So if you play that game, and then you say you evolve, the masses of the binary, you conserve rest mass, etc., you can construct something like this, which is just showing you the remnant mass distribution for a particular choice of weight on each side. And then you can play the same game. You can choose an equation of state. So we chose something that would give a MTOV of 2.2 solar masses in this little exercise. So if you choose that, which is actually pretty conservative given what we see from NICER measurements, for example, you can create sort of, in this fraction, you can sort of see what's going to happen for each binary if this was the actual global binary neutron star mass distribution. So in particular, if you chose MTOV being 2.2 solar masses, you'd get about 50% of binary neutron stars mergers producing a long-lived remnant. So anything that's up to here basically is going to be a long-lived remnant, which is going to dramatically alter the multi-messenger signatures of a binary neutron star merger. So in particular, if you go back to the schematic, it's going to alter all these things, and I'll explain how in just a second. So actually, starting off with jets. So now, jet launching is a big problem. We try to launch jets with numerical simulations, and we basically fail. But regardless, we try really hard, and current numerical simulations suggest that for jet launching, we know that two things have to be satisfied. Two constraints have to be satisfied. One is that the central engine itself must be capable of producing a jet. You can't have a central engine if it can't collimate something, then it obviously can't produce a jet. And then the second thing, which is actually the more constraining one, is that to be a short gamma ray burst, to be a gamma ray burst, something that can actually produce gamma rays, the jet must be fast. It must be a really rapid sort of system, because otherwise you're going to run into something known as the compactness problem. Now, the compactness problem is something that's got a really sort of fancy sounding name, but essentially it's just basically that if the jet is not moving fast enough, any gamma rays that are produced by the jet are actually just going to be reabsorbed. They're never going to make its way out. And so the jet must be moving really rapidly so that you can actually get gamma ray photons to actually come out of the jet. So numerical simulations currently suggest that these constraints can basically only be satisfied with a black hole central engine. So any long-lived neutron star remnant will not be able to launch a jet that can produce a short gamma ray burst. It still may be able to launch a jet. I want to make this distinction clear, but that jet is not going to be able to produce prompt gamma ray emission. So what that means in our toy universe that I've just sort of built up, 50% of binary neutron star mergers would not produce a GRB. And so you might still get this jet, but whatever this thing is, this internal dissipation mechanism, you're not going to observe any GRB emission. But that's numerical simulations. Now, if you're a numericist in the room, I don't see that many actually, you might be like, okay, that's probably right. But if you're not, you're probably going to be like, numerical simulations are always wrong. So you might think, okay, that's what numerical simulations suggest, and there's plenty of reasons why you might be doubtful of that. One of them is basically that we don't have problems launching jets in many, many other systems. So what's unique about binary neutron star mergers? And so this, this is one way to look at it, but another way to look at it is actually just to consider what the data is telling us. And in this particular case, we can have a look at the X-ray afterglow data of several short GRBs that we've already observed. And so in particular, there's plenty of short GRBs, and this is a plot from a really nice paper by Antonio Rollinson in 2013, which is showing you the data of 2 GRBs, but this was on a whole study of GRBs, so there were about 30 or 40 GRBs in this study, just showing you the data, the X-ray afterglow for, in particular, of 09, 05, 10, so short GRB 09, 05, 10, and short GRB 12, 05, 21. And the data is shown in red, and notice that this has sort of this plateau-like feature, and in this particular case, it has this plateau-like feature and a sharp drop in luminosity. It turns out that to explain these two features with synchrotron radiation from a jet, it's actually ridiculously hard. You can contrive various scenarios, and this I could still come up with various ways, but this one in particular is actually ridiculously hard to explain. Anything? Ilya, please go ahead.
Just a question. I mean, I noticed that I presume the red are the data points, right? There are almost no data points during the plateau in either of these plots. Do we actually have observations where, so the plateau is sort of inferred. It could be some totally different shape. It could be a bump going like this, right? In principle.
Yeah.
Do we have observations where we do have data points in that plateau?
We do, not these two cases, but there's actually a really nasty selection effect that makes it quite unlikely that you'll see the data during that plateau, which is, this is BAT burst alert telescope data, and then burst alert telescope tells XRT where to slew, and this is XRT data. So this is the time it takes to slew, and quite often you end up missing this data. So yeah, it's a really nasty selection effect. And so a lot of places you don't actually see that data. Right, so this, as I was saying, it's actually really hard to explain this data with just synchrotron radiation, this sort of thing. But what Antonio showed is that it's actually really easy to explain this data if you invoke a neutron star central engine. And in this particular case, the black fit to the data is this sort of neutron star central engine that's just spinning down to, in this particular case, they chose vacuum dipole radiation. So just simple magnetic dipole radiation. And so in this particular case, there's this neutron star born, it's spinning down and it's surviving indefinitely. So it's following sort of this pathway where it forms a hypermassive object and then an infinitely stable one. Whereas in this particular case, you have a neutron star being formed, and the sharp drop of luminosity corresponds to this neutron star collapsing and forming a black hole. So this is the model. And so now if you trust this, then you can go around and figure out, okay, what fraction of the population follows these sort of things. But now I'll just move on to the next thing and come back to the fractions and just later on in the talk. So coming back to this plot, this central engine, if these models are right, then that directly affects the X-ray afterglow, the GRB afterglow. It turns out it doesn't really make much of a difference in other bands, and that's a peculiar feature that there's many different ways to explain, and I'll go to that if people are interested in question time. But then moving on to the other part, so the kilonova itself. And now the kilonova part is quite interesting, and this is something that I spend a lot of time recently thinking about, is understanding what happens to the kilonova. And the kilonova, the big difference basically comes from the fact that you all of a sudden dramatically increase the overall energy budget of the system. So in a normal kilonova, you have 10 to the 51 ergs of energy. In a kilonova, which has got a magnetar in it, at the heart of it, the available energy in the system is about 10 to the 53 or 10 to the 52 ergs. So that extra 2 orders of magnitude of energy or 1 order of magnitude of energy shows up somewhere, and how it shows up is dependent on a lot of different physics. But you can't just simply just go, okay, it's 2 orders of magnitude of energy, so it's going to be 2 orders of magnitude brighter. It's not how physics works. So understanding how the energy actually translates is something we looked at very recently. And what we found is that it all really depends sensitively on the initial conditions of the neutron star itself. So what I'm showing here is a plot of the external poloidal component of the magnetic field of this remnant neutron star, and a grid of the internal toroidal component of the magnetic field. And basically this parameter space dictates what's going to happen, what's fraction of the available energy of the neutron star itself is actually available in electromagnetic radiation. Because what's going to end up happening is, for example, you have other channels of energy loss. In particular, one of the big channels is gravitational wave emission, because this newly born neutron star is actually going to radiate a significant amount of energy through gravitational wave radiation. So on this plot, the color bar is indicating the fraction of the rotational energy that's available in electromagnetic radiation. And what you end up seeing is that across this sort of parameter space, if you're on the sort of left-hand side, if you have low poloidal... Ilya?
Sorry, I didn't mean to interrupt you, please.
Let's go for it.
Okay, I was just going to ask about time scales, because one of the issues is that it's not about how much energy you release instantaneously, right? Initially, the kilonova is invisible because you're smothered in this very optically thick envelope. It takes, on the time scale of a day, before the envelope becomes sufficiently optically thin that radiation can come out. Now, the reason it works for the kilonova, and similar things for supernova, right, is that you have radioactive decay.
Yep.
Right? So you actually temporarily store the energy in fissile material, which eventually decays and lets out the energy at the right time.
Mm-hmm.
But here, I'm wondering, what is the coupling mechanism, right? So yes, I understand there's plenty of rotational energy available, but what are you going to store that energy in? You don't want to just quickly convert it into a Poynting flux, because that Poynting flux is completely killed off, right? It cannot get out. So what do you do?
You basically couple the energy through some efficiency. That term you don't really understand that well, so you try to model it through, for example, gamma ray escape sort of things, as basically just coupling to the internal shell of material and changing its effective temperature in a way, and changing its internal energy. So that magnetar wind is just changing the internal energy of the sort of little blob that's at the heart of the system.
Right, but then you have to worry about the fact that this blob is adiabatically expanding, and as it does so, the energy is going to drop off as 1 over r, right? So by the time you reach the photosphere, you're still losing a lot of this.
Yep. Next slide.
Oh, sorry.
Yeah, exactly right. What you end up happening is you actually lose a significant amount of energy just to expand the envelope. You don't actually radiate most of it. That's exactly it. This is just, I was building up to that. Basically, in this part of the parameter space, in this region of the parameter space, you end up emitting significant amounts of gravitational wave radiation. But in this part of the parameter space, most of the available electromagnetic energy most of the available rotational energy is actually lost in electromagnetic radiation. But that doesn't mean it gets thermalized, which is precisely next slide. So this slide is just showing that same parameter space again, but showing what fraction of the energy is actually radiated versus what fraction of energy is actually lost in just accelerating the ejector itself. And that acceleration is because you have been pushing this magnetar wind. And so what happens is this color bar is now showing log 10 EK divided by E rad, so the kinetic energy divided by radiated. And so across this entire parameter space, you basically radiate, 100 times more kinetic energy than you actually radiate. So the luminosity of the system doesn't increase by that many orders of magnitude. You end up actually accelerating the ejector a significant amount. But even in this parameter space, the interesting that happens is that the parameter space where you actually most of your energy is available in electromagnetic radiation, you end up making more of it go into kinetic energy, and that's because of basically the ratio of the spin down damping timescale to the diffusion timescale of the system. And so you can think of it in terms of the picture that I just described earlier. If the spin down damping timescale is too small, this ratio is going to be larger. And so if the this ratio is going to be smaller. And if that ratio is very small, most of the kinetic energy of the system, most of the magnetized rotational energy is being inputted into the ejector so fast that it's got basically nowhere to go. Whereas if it's comparable to the diffusion timescale, the timescale it takes for the ejector to actually sort of radiate that energy itself, then it's going to actually basically that timescale is going to be comparable, and so you actually end up radiating that energy as opposed to just accelerating the ejector. And so this is actually something that happens in superluminous supernova as well, and so it's the exact same physics except the parameter space is very different because the diffusion timescale in superluminous supernova is just significantly larger. So with that in mind, it's interesting to look at this grid, but all throughout I've been having these sort of two sort of stars in each thing, and that's just to go through it in terms of a case study itself. And so case one is something which I'm calling a bright kilonova. Now this is not actually bright in all parts of the parameter space, it's just something that I've chosen. And what this system represents is a system where you're having significant amounts of gravitational wave radiation, but most of the available electromagnetic, so significant amounts of gravitational wave emission, but more of the electromagnetic energy is going into thermal and is going to be radiated. Whereas you have case two, which is almost all of the energy is available in electromagnetic radiation, but all of that energy is actually going into most of that energy is actually going into kinetic energy. So that's sort of shown in these sort of two panels. So this, case two is something here. So most of the energy is FEM is quite high, so most of the energy is available for electromagnetic radiation, but most of the energy is actually ending up increasing the kinetic energy of the ejector. And then I'm also going to just show sort of a control, say a kilonova where there was no engine at all. And so this is, for example, the bolometric luminosity, and now I've got a few other features to show in this, but the details are not so important. But what you end up seeing is that case two is, despite more of the energy being available in electromagnetic radiation, it's dimmer than case one. And that's because case one, even though a lot of the energy was lost in gravitational waves, more of the remaining energy was not lost in increasing the ejector velocity. It actually ended up being radiated. But then there's sort of few systematics to deal with, such as, for example, what is the actual initial spin itself, and whether you have something known as like a Pear cascade effect. So the Pear cascade effect is basically initially early on you get a suppression of luminosity from the central engine, basically because all of the energy that's being lost is producing sort of electron-positron pairs, and now these electron-positron pairs themselves have so much energy that they basically end up into a cascading pair production. And so you almost sort of suppress the luminosity early on. And so that uncertainty is shown by these bands here. It's not too important, but it's just to sort of show that even accounting for that little uncertainty, the denominations don't change, in the sense that even despite the fact that you have more energy available in electromagnetic radiation, you still end up producing a dimmer optical kilonova in a case two type system. And that's again because most of the energy is going into radiating, increasing the velocity of the system. And by the way, the dashed and dotted, sort of the dashed curves and the solid curves just represent different initial spins. So that's just showing the uncertainty due to that. And now I've been going on along about basically increasing the kinetic energy, and the reason that that's important is because case one and case two essentially swap. So when you look at the kilonova afterglow, which is the afterglow produced by the ejector, the kilonova ejector itself, the kilonova afterglow only really cares about the kinetic energy of the system. And so what ends up happening is that case one which was a brighter kilonova, an optical kilonova, ends up being a dimmer kilonova afterglow because it has lower kinetic energies. And so if you want to sort of understand whether one thing, if you want to look at, for example, in the next 170817, and you know that there's potentially a central engine there because of, for example, you know, the masses of the binary and they're much lighter than 170817 or something like that. To understand what the initial spin is, you need to fully understand, for example, you need to both observe the optical kilonova and the kilonova afterglow, otherwise you're going to sort of get a misleading picture. So that's sort of the diversity for the kilonova afterglow and the kilonova from a central engine. I've already talked about the diversity of from an X-ray afterglow and a jet perspective. Now we have several different ways of understanding this fraction, the long-lived fraction, because in this toy model universe, I knew what this was, and I could easily say that MTOV is 2.2, so I could say that it's 50% producing long-lived systems. But in reality, I don't actually know what that number is, and so I have to try and infer it. And of course, I could just as easily just wait for LIGO, Virgo, Kagura, etc. to figure out what the binary neutron star mass distribution is, but that's a bit boring because I can do science in the meantime. So what I can do is, you know, there's several different ways for figuring out what this fraction might be. And so all of these you know, this is not an exhaustive list, but this is stuff that I'm personally interested in, I've spent time thinking about. I'm going to go through this, and I'm basically going to say the constraints from current observations, and then I'm just going to say why they're all probably wrong, and why you shouldn't listen to this talk. But you have, because that's the plot twist. Anyway, so fast radio burst host galaxies. So I haven't really talked much about fast radio bursts, but basically fast radio bursts are just these exotic radio transients. And one of the leading models we have for fast radio bursts is basically that it's a newly born neutron star, newly born magnetar that's doing something. We don't know exactly what that is. That's a whole other talk, and then you still might not know the answer. But we've seen sort of a galactic magnetar produce a fast radio burst analog. So we are reasonably confident that many fast radio bursts come from newly born magnetars. But again, the exact mechanism is unknown. There's lots of theories. In fact, until basically CHIME's first observing run finished, there were more theories by a factor of 10 than there were actual observations. So this is a great theory, a great place to put in your theory because you'll basically never be ruled out until CHIME observes even more. So anyway, there's been plenty of fast radio bursts that have actually now been localized. And the localization, the sort of the host galaxy properties and things like the offsets indicate certain things. So for example, there's the first fast radio burst we localized was really consistent with what we see from superluminous supernovae. So that was FRB 121102. And that FRB, the host galaxy, is really consistent, the offset, etc., the galaxy mass, everything really beautifully consistent with what we see from, you know, a magnetar that might be born in a core collapse supernovae. But then there's a handful of others. In fact, there's maybe like 6 or 7 now that are actually consistent with short GRBs. They're well offset, they're in old galaxies, etc. And so there's been a bunch of studies that sort of looked at these things. I'm not going to say that they're, you know, really robust because there's a whole bunch of uncertainties to consider, but they conclude that, you know, the current population of FRBs, where we have offsets, host galaxies, etc., 10 to 20% of those systems are consistent with a short GRB host. So they're consistent with something, with a magnetar that might be formed in a short GRB. So consistent with a long-lived neutron star being formed in a short GRB. Now, whether that neutron star is infinitely stable or not is another layer of question you have to sort of ask yourself. Rate-based estimates would suggest that basically, because of the all-sky rate of FRBs, they would almost have to be long-lived, infinitely stable systems because each of those systems has to produce many FRBs over their entire lifespan to explain the all-sky rate of FRBs. So, you know, whether they're infinitely stable or not, I'm not going to go into too much detail, but they probably have to be. So take that as 10 to 20%. producing stable neutron stars. So this is my picture. This is a made-up universe, but FRB host galaxies are telling us that 10 to 20% are stable. The other game you can play is actually just look at the jet launching fractions. So I mentioned earlier that numerical relativists believe that you can't launch a jet, you can't produce a gamma ray burst unless you have unless you don't have a long-lived neutron star, basically. So what you can write down this equation, which is just saying that the rate of short GRBs is some fraction of the rate of binary neutron star mergers that can launch a jet, times a beaming fraction, so the fraction that are actually beamed towards us, because gamma ray bursts are strongly beamed, so they have to be beamed towards us, times the BNS merger rate, plus some fraction, some contamination from NSBH, because some fraction of NSBH could also produce a jet. So we played this game, and so by the way, FS, BNS, are the fraction of BNS and NSBH that launch a jet. And so you can write down F long-lived as just being 1 minus FS BNS, because that's the constraint that's being put in suggested by numerical simulations, that if you want a gamma ray burst to be launched, to be produced from a binary neutron star merger, you can't have a long-lived system. So we did this for a completely different reason, but I just decided to turn this fraction around. And so what we can do is, we did this in a recent paper, and we derived constraints on, for example, FSBNS. And we found that it was about 0.7 plus or minus 0.2 using current measurements. A lot goes into it, and I'm not going to go into too much detail because the only thing I care about at the moment is this jet launching fraction. So what that tells us is that since we measured it to about 0.69 plus or minus 0.2, the jet launching fraction, as suggested by this sort of current measurements of LIGO, Virgo rates, etc., is 10 to 40% are long-lived. So 10 to 40% of BNS mergers must be long-lived, otherwise you got an incompatibility between the rates of different things. So then there's the other thing, which is actually just following up radio short GRBs, follow-up radio of short GRBs on doing optical and radio surveys. And that's because, as I showed this plot earlier, when you have no engine, it's a much dimmer system than when you have an engine. Even regardless of what the specific properties of the engine are, it's just going to be significantly dimmer than the other ones. So you can just follow up short GRBs, try to find a radio remnant, or you can just do an all-sky survey, try to find the radio remnant, or you could same thing for the Kilonova side. If you just do an optical survey, you can try to find a radio remnant. So there's been actually multiple places where this has been done. So the most sort of recent one, and the one I'm sort of the biggest fan of, is this paper by Schroeder et al. And this plot is actually the one that I find particularly interesting, because this is just showing. So just for a little bit of context, what they did in Schroeder et al. 2020 is basically followed up every short GRB with VLA and something else, I forgot. With every short GRB in the local, up to Z of 0.5 or so, and try to find out if there was a radio remnant, because if there was, given current constraints of sensitivity limits, etc., it would have to be a magnetar central engine, otherwise they wouldn't have seen any radio remnant at all. And so what they found with that in following up all these short GRBs is that the F long-lived fraction must be less than 40%, just because they found nothing. Ritchie et al. Also did the same thing, and they found a slightly different number, and this is a lot into the different modeling assumptions that go in, and I'll go through those later on. But the other interesting thing that Schroeder et al. Did is actually just sort of predict, based on how many fraction of stable remnants or long-lived remnants there will be, of how many transients we actually expect in the VLA all-sky survey. And so this is just a plot showing the number of VLA all-sky survey transients that you would expect to see as a function of the stable long-lived fraction of neutron stars. And so from short gamma ray bursts, they can already say that it's lower than this number, and that's again just related to this constraint. And so what they can do is they can say, okay, if VLASS doesn't see any radio remnants at all in its survey, radio remnants of short GRBs of binary neutron star mergers, then we know that F stable must be lower than some number. And again, this number depends exactly on what the ISM in the stellar medium density is, because that sets the brightness of the survey in a sense. But really marginalizing over that a little bit, currently we have no radio remnants in the VLA survey. Consistent with a BNS merger. I think we have one consistent with something else. And so since we have none, we can already say that, all right, given what we expect typical ISM merger densities to be, the F log live fraction must be less than 10%.
So, Nikhil, this VLA survey, is it sensitive to any magnetars? So my question is, if you believe that the FRBs are being launched by magnetars, right? Then whatever is responsible for creating this magnetar, whether it's a binary star merger or just a neutron star that happens to be born with a huge magnetic field or some other very exotic mechanism, whatever, right? Don't you have is there at some point an issue that if you're not detecting enough magnetars, then you're struggling to explain even the model where the magnetars are launching FRBs? Forget about binary star mergers?
Yep. So we're definitely going to end up in that problem. Yeah. Okay, so tallying all that up, we've got 10 to 20% from FRB host galaxies, jet launching fractions suggesting 10 to 40%, radio follow-up suggesting 10 to 40%, less than 10 to 40%, and then you have X-ray afterglows, which I discussed early on. So, Antonia's done this in 2013. Paul and I have done this in other times, and several other people have done this in other places as well. You can basically just look at what fraction of short GRBs have these features. And so what we find is that 20 to 30% of short GRBs have this plateau-like feature and then no decay at all, which is indicative of, in this model, of an infinitely stable neutron star. And then 20% of short GRBs have this sharp drop in luminosity, and which is indicative of a supermassive system. So tallying all that up, you've got this list of numbers written there, and really, you've got a tension between all of these, and understanding why there is a tension. If you believed all these ingredients that I've put in, you'd be like, okay, this is a really big problem. But it turns out you shouldn't have believed any ingredients that I've put in, because there's a lot of systematics you have to deal with. So for example, when you try to infer what the radio remnant brightness is, given that it has a magnetar in it or not, you have to assume a whole bunch of parameters. And so in these studies, they assume, for example, that the equipartition, sort of, equal amounts of energy is going into the electrons and equal amounts of energy is going into the magnetic field itself to produce synchrotron radiation. You also have to assume what the ISM density is as well. And so one systematic that I'm just showing here, for example, is that you don't actually know what the ISM density is. And so even if you have an afterglow measurement, you still have an order of magnitude, at the very least, uncertainty in your ISM density, which can cause this band of uncertainty in the brightness. And so if you observe something really early on, then that's fine. But if you observe anything, particularly after it decays, then that uncertainty alone can create big issues in trying to distinguish between these two things. And then you have other uncertainties, for example, like in the microphysical parameters, such as how many electrons actually participate in synchrotron radiation, what the fraction of electron energy is and magnetic field energy is. And really, the point I want to stress is that unless you're capturing things very, very early on, at the rise, much earlier, it's going to be basically impossible to distinguish these three scenarios after it peaks, because there's so much uncertainties in afterglow modeling that it's very hard to try and do this. The same thing actually goes for kilonova modeling. So all throughout, I didn't actually show this particular plot, but this is just the bolometric luminosity converted into G-band, R-band, I-band, and that's just because of choosing it because of ZTF. And what I'm showing you here is basically this dashed line and the solid line are the exact same parameters, but just different assumptions about how the ejecta is distributed. And so in kilonova models, for example, for 170817, we typically took this approach where there was one solid component corresponding to the blue ejector and one solid component corresponding to the red ejector, and we just added them up and we didn't do anything else. But for example, let's assume that there's some more interplay, or there's actually a distribution of velocities and opacities, etc. Then if you have the same parameters and you make a model where there's actually just one component, and you make a model where there's actually a distribution of shells with different opacities and velocities, then you can just get this little uncertainty. So the dashed curve and the solid curve are the exact same parameters, is just a different assumption of about how the thing is distributed, how the ejector is distributed. Then there's other uncertainties to consider. For example, as I was mentioning, the jet is actually making its way through the cocoon, the ejector, and actually heating up the jet. Nobody models that exactly. And so if you're viewing a system close to the line of sight of the jet, which is, for example, what we were doing with 170817, we were not exactly aligned with the line of sight because we were a little off axis, but we were still, within that sort of polar ejector sort of region. And so what that jet interaction does, nobody really models that very well. Then there's the other big source of uncertainty is actually how much energy does each gram of our process material actually radiate. Everybody in the community is actually very happy to use this sort of model from Cocoon et al., which is just saying that for every gram of material, you get 4 times 10 to the 18 ergs of energy per second. But actually that 4.0 ergs of 4 times 10 to the 18 ergs of energy is actually not certain at all, because it depends on our process nucleosynthesis calculations, which are not done in significant enough detail. So if that number is different, if that number has such as, for example, actually Zhu and Barnes in different papers, they actually showed that just given current estimates of the uncertainty from nuclear heating alone, you can basically get an order of magnitude difference from just uncertainty from that alone. Just the uncertainty from the nuclear heating gives you an order of magnitude uncertainty at peak. And so if we're not seeing something early on, again, it becomes really difficult. And this is quite early because these magnetar systems are really rapid. For context, 170817, we first observed 11 hours later. And so that is ballpark, where is it? 11 hours is somewhere down there, I guess. So that's systematics to do with kilonova and kilonova afterglows. Then you have systematics to do with X-rays themselves, the X-ray afterglows themselves. And there's sort of two systematics to deal with. One is that you can actually explain, as I was alluding to early on, this part relatively well if you invoke structured jets. And we know that jets are structured because we saw for 170817. But what that implies about the population of GRBs is actually quite interesting, because the only sort of sensible way to get this feature in a structured jet is assuming that you have an extended sort of, if you have an ultra-relativistic core, and instead of viewing the jet as you would canonically in a gamma ray burst along the line of sight, such that you're seeing the gamma ray burst, you're actually viewing the jet from a little bit further out. And so you're still within the sort of extended material of the jet, so the extended structure of the jet, which is what's leading to this plateau-like shape. But you're not actually within the ultra-relativistic cone. And now, if that's true, then our current understanding of gamma ray bursts sort of falls apart a little bit, because gamma ray bursts, a lot of the ones we've seen, especially the ones with these sort of features, would not be us staring down the barrel of the jet, would be staring down a little bit much more further out. Not even the opening angle of the ultra-relativistic core, we'd be much further out again. This part is actually what I'm calling binning is sinning as a systematic, which is basically a lot of these sort of modeling, including by myself, was done with the automatic generated Swift data. And so basically what Swift does is it observes a bunch of photons and then automatically bins it to create this looking little light curve. But actually, the choice of binning doesn't actually apply, and it's not valid for every single different transient. And so if you bin this thing slightly differently, this data point might end up here. And so all of a sudden, this thing is not actually a sharp drop, it's just a gradual decay. And so binning is sinning. So I went through all of the different little systematics, and so I want to just conclude, and I think the time is reasonably good for questions, I think, Rio. So what I would just want to say is that actually it turns out, and this is what happened in 1708-17, everybody was very happy to invoke gravitational waves as a place to hide energy, and so invoking engines when they potentially weren't, basically because you can hide energy away from the system. And gravitational waves, if they're sourced from a magnetic deformation, are actually a terrible place to hide the energy of the central engine, because that's precisely the parameter space where the remaining energy is going to be thermalized. More of the remaining energy is going to be thermalized. You actually want to hide the energy in the kinetic energy of the system if you want to avoid kilonovas, the optical kilonova being much more ordinary as opposed to a bright one. And because of all the systematics, in the absence of spectra, combining both the kilonova and the kilonova afterglow is actually the best way to try and figure out if there is a remnant, because alone they have so much sort of individual systematics to deal with that you're always gonna end up having some issues. FRB offsets, jet launching fractions, all of these different channels are sort of giving us conflicting answers, and the answers may just be systematics, but it's another interesting way of just understanding what the binary neutron star mass distribution looks like. And as Ali alluded to, it's potentially creating issues already, in such as, for example, the FRB model we invoke and other things as well. And so, yeah, with that I'll conclude and take any questions. Thank you so much.
Yeah, really early in the talk, this is more of a fundamental question. You said specifically that differentially rotating neutron stars are more stable than, say, a solid body rotation neutron star. Can you explain why that is?
Basically, it just comes down to differential rotation adding more support than rigid body rotation itself would. And that's just because if you just go through the, if you've got a system which is, each shell is sort of rotating at a different velocity, you end up having more centrifugal support than if you just had a solid body rotating at a velocity, rotating at the same velocity.
Cool.
So did you think about phase transitions possibly in the equation of state, or maybe even a transition to quark stars possibly could induce some phase transitions during the collapse early on when the matter is very hot, and then could put you in a different regime and domain and maybe make different masses of black holes?
Not specifically to the last part about making different masses of black holes, but we actually wrote a paper which was exactly that title in a way of what your question was, which is basically gravitational waves or deconfined quarks, what causes the premature collapse of neutron stars. Because what was happening is, if you go back to this plot, all of these collapse times were happening way too early on. So, there's about 18 systems. We found 18 systems where this collapse is happening around 100 seconds, 200 seconds or so. And if you assume just pure vacuum dipole radiation, it should be actually a pretty broad distribution. Again, it depends on the initial conditions, but it should be a broad distribution. And so Paul wrote a paper suggesting this distribution, and then a handful of other people said, all right, this distribution doesn't make sense. Either it's gravitational waves causing this early spin down and early collapse, or it's deconfined quarks. So a phase transition in the course of the merger producing deconfined quarks, and so you just end up collapsing early. What we found when we did sort of the inverse problem was that there's one sigma preference with the current data that they are composed of deconfined quarks, but at the same time, most of the systems are also spinning down significantly through gravitational wave emission. So the answer was both in that case. And yeah, if that phase transition is true, if it is happening, it almost certainly has to be happening during the course of the merger, because the equation of states that are sort of supported by this sort of data are sort of incompatible with what we're seeing with NICER and stuff. So the fact that those measurements are incompatible would almost suggest that you have to have a phase transition during the course of the merger itself. So the hot, newly born neutron star is different to the cold neutron star that NICER, etc., are observing.
So looking at my follow-up question, so as your neutron star spins down, so you would not expect that you would have a phase transition during that spin down phase where you transition from one phase to another, and this kind of transition then possibly gives you a shock and mass injection, because we currently we have been looking at some phase transitions happening during core collapse supernovae, and there being a secondary shock that can affect the supernova explosion itself. But I could imagine that phase transitions could also happen. If they were to happen in such spinning down neutron stars, you could get some kind of transients that is not yet the final state, and if the star spins down, you could have a second gamma ray burst or second transient event coming out of the same object, and it finally collapses to a black hole.
I think that's interesting. The only sort of thing I have, potential issue I have with regards to this context is that the remnant is spinning down incredibly rapid. It's spinning down, initially it's spinning down incredibly rapidly, and it's also cooling really rapidly. So what the conditions were that caused the phase transition in the first place actually evaporate relatively quickly as well. So you would have, I would imagine, I'm not sure, it'd be interesting to talk about this more, you would basically lose the conditions that caused the phase transition in the first place pretty quickly. And would that be compatible with the time scale required to explain a feature like this? I'm not so sure, because the remnant is cooling down on from 10 to the 11 MeV down to 10 to the 11 Kelvin down to 10 to the 9, 10 to the 10 on time scales of a second or so. So yeah. I'm not sure. It's interesting. We should talk about it more.
Any other questions?
Sorry, why do you say that nicer rules out equations of state with the confined field? So I thought that the maximum mass is like 2.1 more or less.
Yeah. No, sorry, that's not what I mean. I don't mean that nicer rules out quark, deconfined quark equation of state. I'm just meaning that the equation of state that would satisfy a premature collapse like this, so the equation of states that could give you a premature collapse like this are ruled out because they're very different to the nicer ones. I think Ang Lee et al. Have subsequently then turned the knobs again. I think they've managed to find another sort of thing, but I think the ones that we used in that paper would all be ruled out by nicer constraints, I'm pretty sure. But yeah, that's not to say that nicer themselves are ruling out.
How realistic is it actually that your unicorn neutron star is rotating faster in the interior than on the outside?
How important is it?
How realistic is it that this will actually occur rather than having just solid body rotation?
So we see this in a lot of numerical simulations, that this is what's happening. There was actually a recent paper by Ben Marglit showing that if you have sort of difficulties transporting angular momentum between the inner and outer shells, you'll actually end up in situations where you get a premature collapse. Even though it was in the 1.2 times MTOV regime, it would still collapse on differential rotation timescales. And that's because you've not been able to efficiently transport angular momentum from the outside to the inside. So it's definitely very important. We're basing this off numerical simulations and understanding so far, but I don't think it's definitive exactly what's going on.